The following program is brought to you by Caltech.
Okay, I'm going to introduce Carver Mead, and people who know me know that I don't like long introductions. Usually people introduce me, and I don't like it when they take a long time. So my introduction will be brief. I will not tell you anything about what he has accomplished, because all of you know it. I won't tell you anything about all of his awards, because there are too many of them. I mentioned this morning the Medal of Technology, but it's only one of many. I just want to tell you what comes to my mind when I think of Carver Mead. And when I came to Caltech, within 2 weeks, I had the fortunate opportunity to have dinner with Carver. We met at your favorite restaurant, and you invited me, and we had drinks and dinner and a little bit of wine. We did well. And I have to say that I learned a lot about Caltech during that dinner, and it had a profound impact on me. And with all due respect to many of my colleagues who are here tonight, it was the most important discussion I had about Caltech during my first few months here on its campus. Carver told me about why Caltech is special, told me about unusual people, a commitment to excellence, creativity, focusing on those activities which are across the boundaries. Everybody is talking about it nowadays, but Caltech has been doing it for many, many years, and keeps doing it very well. Told me also about the opportunity of resting or standing on the shoulders of giants. So he told me about the values and the culture of Caltech. But what I realized, and since then we have become good friends. In fact, he's even a closer friend of my wife, because sometimes they have lunch or dinner without me, and then that's true. And I believe that there is nobody at Caltech who embodies more the values of Caltech than Carver Mead. And, Carver once said, "We have no system for corralling people at Caltech. Thank God we don't. That's why I'm still here." And we are so pleased that you are still here, Carver. His cross-disciplinary endeavors and connections have led to new ideas, new inventions, entirely new fields. And one of them, which I mentioned this morning in my remarks, obviously, is his interaction with Gordon Moore, which led to lots of important discoveries and new businesses and so on. And Carver described it sometimes as a good mutual back scratch, if I remember that's what you said. And that good mutual back scratch really helped create the new information age. Carver has also been a great entrepreneur. I think he has helped found something like 20 or 21 different companies during his activities at Caltech and elsewhere, and developing a large number of innovative new technologies. So when you think of Caltech, I think about people focusing on very difficult, fundamental problems, but also people who think about what can be done with them. How can we do for society and solve important issues society is facing? And Carver really embodies that. And we talked about standing on or at least I talked about standing on the shoulders of giants. Carver took physics from Feynman and chemistry from Linus Pauling. To me, it's like taking soccer from Pele and painting from Picasso. But what is more important, after he stood on those shoulders, many, many people after that stood on his shoulders. And some of you are here. I know. And to give you a sense of that, and to show you that Carver has shared his gift with several new generations, again, a quick study shows that I believe currently his former students have created more than 100 different new businesses, new companies. You know, Carver has had an amazing accomplishment as a scientist, as an engineer, but even bigger accomplishments, I believe, as a mentor and as a person who cares about people. Carver Mead, your speaker tonight.
Thanks, Jean-Loup. With an introduction like that, I don't really have to have much to say, so we can leave it at that. But I thought, after hearing the talks today, which were really neat, it might be good to go back and just think about the last 100 years and what it was like then and what we've come through and what it might be like in the future. 100 years ago, when EE was founded, Rael Sorensen chose electric power as his area of research. Now, in a way, that was an unfortunate choice, looking at it from today's perspective. Electric power California had a particularly acute problem with electric power. The sources of power in those days were water running down from the high mountains to the Sierra Nevada. And the places that needed electric power were Los Angeles and San Francisco, some 100 to 150 miles from where the energy was. And so the need arose not just to generate the power, that was well known at the time. The need arose to ship the power over 100 miles. That hadn't been even remotely done before on a production scale. The amount of power you can send over a wire of a given length with a given loss of energy goes like the square of the voltage. So the only way you can transmit electric power over large distances is at very high voltages. The only way that you can build a system with wires at high voltage is to insulate them from the ground and the towers that hold them up and that sort of thing. So starting in 1889 with the first high voltage electric transmission, which happened between Oregon City and Portland, Oregon, there was this incredible drive to go to higher and higher voltages to send more power further from its source. And California was driving that effort. They were relying on a bunch of East Coast entrepreneurs and technological fanatics, and it was a very tumultuous period. But between 1889 and 1909, we went from not being able to do anything but relatively low voltages, a few thousand volts, to having basically what amounts to our modern art form. Suspension insulators. The problem with the early insulators was that to insulate against higher voltages, you had to make them bigger. Well, in 1907, the insulators were about this tall, that big around, and weighed about 70 pounds. It took a very burly lineman to even get them up there and get them bolted onto the tower. But that wasn't the end of the problem. The problem was any tension in the line would exert a huge torque on the pin that was holding up the insulator, and that would, under storm conditions or whatever, would bend the towers, and then the lines would short out. And it was a constant problem to keep lines in service. Then a big innovation happened in 1907. That was the invention of the suspension insulator, the thing you see in little discs hanging from the ends of all the power towers today was basically a very simple idea. Don't try to put something up on a pin and where it can be torqued around by the line. You make a plate that's insulated, the top from the bottom, by a piece of porcelain or glass, and it will withstand, let's say, 10,000 volts. If you want to run the line at 20,000 volts, you put two of them in series. And so you can insulate against basically any voltage you want in this perfectly scalable way. Nice, scalable solution. That was 1907. First line was put in between Stanislaus River and Mission San Jose. 1908, there was a little longer line put in. And then in 1909, something extremely important happened. That was in the Carolinas, using, once again, suspension insulators, running at 120,000 volts or so. It was the first power grid. The power systems out here were always point-to-point systems. They ran from Big Creek to Eagle Rock and things like that. But back there, they had little cotton mills and things everywhere. So they developed a real grid. So by 1909, we had gone up the S-curve of innovation in electric power. We basically had a version of the technology that's ubiquitous today. And it was in place. And what was left was to go from 120,000 volts to 150,000 volts to 220,000 volts to where now there are megavolt lines in service. It was very unfortunate because Royal Sorensen came on the scene just after the big innovation had happened. He missed the 20 years where we went from not knowing a bloody thing about it to having basically our modern art form. It was a thrilling time. It happened here in California, and Caltech missed it. Doesn't sound like an auspicious beginning, does it? So you might think, well, maybe we just fumbled the whole deal. But after World War II, things changed, and they changed in a way that very hard for those of us who lived through it here to identify. But what you can do is you can look back and you can say, what's the difference between what it was like at World War II and what it's like today? I can do that because I was here during that period. And the big difference is today we have basically all over the world a vast number, an astounding number of highly capable computing devices made out of semiconductor chips that are all linked together. And that network of interconnected computing devices touches the lives of almost every human being on the planet. It's by far the biggest change of any kind that has ever happened to humankind. So, in aggregate, that's a big thing. Did we have any part in that? Well, that's an interesting question. On the semiconductor side, my first experience with electronics was with vacuum tubes. And when I was a high school kid, I read about this transistor thing the Bell guys had invented. What I didn't realize was Caltech alumnus Bill Shockley had basically out of whole cloth, invented the semiconductor physics viewpoint and way of looking at things and some of the devices that came along. And that's what we've been living on ever since. Absolutely fundamental to everything we do. Wasn't seen that way at the time, but that's what it turned out to be. Then, of course, as Jean-Loup pointed out, Caltech alumnus Gordon Moore has probably done more than any other single human being to take that basic technology and bring it to the world through first Fairchild Semiconductor and then through Intel. And many of you have had various associations with Gordon and his companies. It was interesting when Gordon first observed that the economics of semiconductor manufacture drove you to put more capability per device. Now, of course, there was a small hurdle to get over, and that is how do you make devices on the same piece of silicon so that you can make a circuit out of them? They aren't all just shorted together by the substrate. That was Bob Noyce's invention of the integrated circuit. Once they had figured that out, then it was very clear if you made more of them and you could hook them up, there was more value per item that you had to manufacture. And that was the beginning of what came to be later called Moore's Law. You would have thought that once Gordon had said that, which he did in 1965, in a nice little article, which many of you have seen, you would have thought it would have just been obvious to everyone. Wrong. Because there were a whole bunch of papers out there that said the transistors are already getting so small that this or that or the other catastrophe is about to overcome us, and they won't work if you make them any smaller or crowd them together anymore. And there were at least 20 reasons advanced why you couldn't go beyond the scale at which transistors were manufactured at the day. So it was common lore that you just couldn't do that. So it was left to people on the campus to go back and figure out the physics behind these things and figure out how small you could really make these things. And it turned out that after some people looked carefully at that there really wasn't anything that was going to get difficult until it got to be like 1/10 of a micron. In those days, they were 10 microns. So that was a factor of 100 in size, a factor of 10 to the 4th in density. Well, you may imagine that there was a fair bit of hornet's nest stirred up over observations like that, especially when it was pointed out that if you scaled the devices smaller and you scaled down the voltages and other dimensions in the right way, that everything got better. The devices got faster. The power density didn't change. So a given size chip would continue to dissipate a given amount of power per unit area. And everything got better. That was, of course, you know that Murphy never goes on vacation, but he did. So that was a violation of Murphy's Law. That was amazing. That was a hard sell. And in the process of all this, Caltech took a very active role in not just the physics of the devices, but also in how you design them. What do you do to design something with 1 million working parts? That had never been done before. So how would you go about that? Things like if you're going to be making devices like this, they're going to be complex. They're going to do a lot of computing. They're going to be everywhere. So they have to be connected. So the prognosis was made right here on campus that the communication industry and the computation industry weren't going to be separate. This was going to be one big technology. That was, many of you remember, during the days when there was a consent decree from the Supreme Court that said that computation and communication would forever be separate. And if you did one, you were not allowed to do the other. Well, if we look out in the world today, that's not quite how it is. The other observations that were made right here on campus were that, the set of talents that it takes to manufacture semiconductor devices, incredibly precise and exacting chemical process. And the talents it takes to do that are really different from the talent it takes to understand a large computation and communication system. So sooner or later, they'd be done by different groups of people. That was not a popular comment in the semiconductor industry. And it has ended up now that what's now called the fabless semiconductor model of doing business accounts for roughly half the value that's created in semiconductors today. So there was a whole lot more going on than just technology. It was about how it fits in society, how it fits in business, and that sort of thing. So enough's been said about integrated circuits and computation. I think we heard a lot about it today, a lot of wonderful, wonderful things going on. But what about the communication side? Well, in today's world, as you all know, communication is done by laser beams going over fiber optic for a backbone, and then RF radio links with sophisticated encoding of digital data for the last spread at the end. So did Caltech have anything to do with that? Well, actually, yes. Caltech alumnus Charlie Towns proposed the first stimulated emission device, demonstrated that, wrote the book that analyzed that you can make masers and lasers. And when he was proposing this, he went to both Bohr and Heisenberg. And they both said, in effect, Sonny, you just don't seem to understand how quantum mechanics works. Amnon and I were having dinner a while back, and we were talking about this, and Amnon said, yes, and we never bought it. The whole statistical garbage about quantum mechanics just isn't physics, that's all. So we never bought it. And Charlie didn't buy it. So he went ahead and made the first maser. But even the early lasers aren't really suited for a communication system like we have today. They don't really fit nicely in a fiber optic environment. The lasers we use are semiconductor lasers. Well, where'd that come from? Well, the first semiconductor laser, as you heard from Amnon today, was built by Caltech alumnus Bob Hall at the GE Research Lab. And of course, immediately afterwards, everybody jumped in and did that. But Bob, Caltech alumnus, did it first. Bob has been under-recognized for that achievement, for I think largely political reasons. Of course, those early semiconductor lasers weren't nearly good enough, and so it fell to Caltech faculty member Amnon Yarev to invent the distributed feedback laser that he told you about today, which was actually up to the job. And that's what we have. 3 Caltech people in series it took to do that one. So it must have been tougher than the integrated circuit stuff. Well, but what about the end? We have sophisticated digital codes on RF links. Did Caltech have anything to do with that? Well, as a matter of fact, yes. I think you would all agree that the effort that really hatched the fundamentals under our communication technology of today started in Caltech's very own JPL Deep Space Network. A bunch of incredibly talented people that basically, out of whole cloth, came up with what's recognizable as the precursor to our modern art form. That's pretty amazing. We're very fortunate that because we're so close to that effort, it lives on in EE today, and that's wonderful. So here's the biggest thing that's ever happened in the human race. And here's a little tiny institution that when you go and look at the really fundamental shifts in thinking that led to this thing we call the information revolution, Caltech is front and center in every aspect of that. So why is that? What was there about Royal Sorensen's blunder that led to this Caltech being there when there's these big paradigm shifts? Well, I would propose that the biggest gift that Royal Sorensen gave to Caltech is he had a different view of engineering than other schools did. Engineering wasn't something you studied and learned and memorized and knew where to look up. Engineering was understanding things all the way to the bottom, no matter what field they were called, and being able to use that to build stuff and make it work. And so we had wonderful graduates from Bill Pickering was mentioned as Cy Ramo. And from there on. Fortunately, I've got to hear some of the younger people today, and my gut feeling is that's still happening here, and it's neat. Now, I talked to Jean-Loup about tonight. I could stop right there. But he said, why don't you talk a little about the future? It's always dangerous, of course. A lot of crosses on that graveyard. But I think some things about the future are clear. There's a bunch of stuff needs to be done in energy. A lot of it is going to require a shift in viewpoint. A lot of it's going to require people getting their heads around more than a tiny little slice of the field. Harold Rosen gave a great talk today about, well, what if you just thought about it different? Well, yeah, you could double the amount of transportation fuel you got and get electric power out of it too. That's the kind of thinking I expect out of a Caltech person. So I think, yeah, there's lots of challenges in electric power. Again, now, we're going to go through another one of those. It's going to involve a lot treating the information and the power not as separate things, but as the same thing. In the same way that FedEx says the important thing, the information about the package is just as important as the package itself. Okay, we need to do that with electric power, and yeah, that needs to be done. The seeds of that are already going. I don't think, to me, that's not really future. That's today's work to make it so that it'll actually be there 50 years from now. It takes 50 years in a field like that. And that's not just because people are stuck in the mud and move slow and all that. It's because if it goes wrong, you don't just reboot. It takes a substantial part of the country down. So you don't just play with it the way we do with software. It's not that kind of a problem. So it is going to take longer. But make no mistake, there'll be Caltech people there, and they'll be there when you need to put it together in a different way and make it work. But that's, in a way, kind of obvious. It's being worked now. There's a lot of resistance to it. But heck, there were a lot of resistance to this other stuff, and we managed to get it through. So what about further out? Well, in the general area of computation and communication, Amnon mentioned it briefly today. People are just now starting to do radio techniques at optical frequencies. And that's really exciting. This whole idea of statistics and quantum mechanics is being shown to be as brain dead as it always was. And that's just wonderful. I read a paper the other day by Ted Hench, who's a good friend of the family here, and they have an optical fiber length between two of their sites, and the coherence length of the photons in that fiber length is 10 to the 8th meters. So much for statistics. Yeah. The role statistics plays in quantum systems is what we engineers used to call noise. So that's playing out, and we're getting finally a sensible view of what quantum systems are, not some statistical garbage but they're nice systems that have the properties of waves that we engineers understand. We know how to work with those. And like Amnon says, we never bought it. So that's why we could keep going. Then if you look a little further out, there's one that has been, somebody said today, I think maybe it was Arthi, that's the wave of the future and always will be. I've busted my own pick on this one, so I'm sensitized. We know that the brains of animals can do computation tasks orders of magnitude better than our biggest and most power-hungry computers. So what are they doing? Been a lot of progress in the last 20 years. CNS was a spin-off of EE that was founded in order to grapple with that issue, among other important issues, but that was sort of the central one. That's still an important issue. There's a lot known, and every time we learn something more, we find out it's even more complicated than we imagined. And it keeps doing that. Just for example, people used to count neurons and compare them with gates in a logic circuit. Okay. Then they realized that those neurons were all hooked up to these little synaptic connections. And as we probed around in there and looked at it more, we found out that, there's some information processing going on in those little things. Well, okay, we can count synapses. Those are like gates. So we started counting synapses. Of course, there are 3 orders of magnitude more of those. So then the brain just got smarter, or the people looking at it got a little less stupid. So now people are looking at the synapses and they're realizing that, they have both long-term and short-term memory in them. The long-term memory is through some kind of DNA replication process that gives it a permanent change. Oh my gosh. So the number of state variables are really the number of molecules in there, and the number of connections are like the number of reactions between these things. And that's just in one synapse. There's a lot more going on there than we know. Figuring that out is going to take a while. And as you might expect, there's a bunch of Caltech people working on that. Other people at other places too, but there's a lot of people here that are doing good work in that area. I've only talked tonight about things that I have some grasp of. There's a bunch of other things going on at Caltech that I admire enormously, just don't know enough to talk about. But I can tell you one thing with great confidence. This is an observation that I'm not afraid to make as a prediction. That is, we can see these things in the future. The nearer term things like the energy stuff, the slightly longer things like what people are now calling quantum computing. It's a bad name, but it's got good press, so they go with it, That's going to take a bit longer. And then there's stuff about figuring out the brain, and that's going to take a lot longer. But has a lot of potential, too. But I can be very confident when I say those things are going to be important. But in the same way that Royal Sorensen didn't see information as a thing he could put his life work into, right now, today, we can't see the thing at all that's going to be the most important 100 years from now.